All right, so I gave you guys a picture. Were you guys impressed by the pictures that I put in here?
Yeah.
Because I was like, I'm awesome. They're even better if they're in color, but, you know, budget and all that. All right, so a television camera is down here at ground level, filming the liftoff of a rocket that is rising vertically according to this equation. So instead of us searching for a formula, they gave us a formula. That was nice of them. We also have a right triangle. So, you know, the Pythagorean theorem will probably come into play at some point. All right. S is measured in feet. T is measured in seconds. The camera is 2,000 feet from the launch pad. You can see that the 2,000 is kind of dark, but it's labeled right there. Find the rate of change in the angle of elevation of the camera. So you can see the angle of elevation is written as theta. So that means that we are going to be finding d theta dt. Okay? 10 seconds after liftoff, that means that t equals 10. Okay. So the first thing that we can find, it says s equals 50 times t squared. This is side length s. So if I want to know the length of s, I just have to take this equation and plug 10 in, because 10 seconds after liftoff. Okay, so I'm going to say s of 10 is 50 times 10 squared. So we have 50 times 100, 5 times 1, which is 5, and then 3 zeros. Did you guys see how I did that without a calculator? Okay, so 50 has 1 zero, 10 squared is 100, that's 2 zeros, 5 times 1 is 5, and then I had 3 zeros after it. Okay, so 50,000, what are the units? Feet. Okay. All right, so now we have a triangle going on here. It might be beneficial for us to have the third side length of the triangle. This right here, tan theta equals s over 2,000, that is not the side length of the triangle. Okay? That is them using SOHCAHTOA to give you a relationship to find this angle. Does that make sense? Okay. So what letter would you guys like to call this dotted line right here?
X.
X. I'm going to go ahead and just use H. What does H stand for? Hypotenuse. Marvelous. Okay. So we're going to say 2,000 squared plus 5,000 squared equals H squared. And so H squared equals, it's going to be a lot of zeros. Actually, we're going to be using calculators today, so if you want to go grab a calculator.
No. That's 4 million plus 25 million.
It's 29 million. Yeah.
How many zeros?
Say it again? Because it's not a rate, it's just a length. The reason is because distance is rate times time. So if you think that your rate is feet per second, and then your time is seconds, your feet per second and your seconds cancel, and then you just get feet. All right, so if you plug that in, you get 29 million. Then H is the square root of 29 million. I do not want whatever nasty decimal that's going to give me. So I'm going to just use that. Okay. All right, so let's write down all the things that we know.
Oh, that's not bad.
We know that T equals 10. I'm going to call this X. Are we okay with that? Okay. We know that X equals 2,000 feet. We know that S equals 5,000 feet. We know that H equals the square root of 29 million feet. That's cool. We know that d theta dt, the rate of change of the angle of elevation, is what we're solving for. we know that is that all we know? I think that's all we know. Okay. All right, we know, I'm going to write it up here, that S equals 50t squared. So if this is the position equation, this tells me the position of the rocket, how do I find the velocity equation so I can see the rate of change of the position? I'm going to take the derivative, okay? So the derivative of S is 1 times ds dt, right? So every time we take the derivative of a variable, we always tack on the d whatever dt on the end, right? So the derivative of a plain variable is just 1, and then the derivative of s would be ds dt.
So in theory, could you just write ds dt?
Yes.
I'm sorry, can you say that one more time?
So I said anytime you have a variable, like an x that's alone, the derivative of that would be 1. A t that's alone, the derivative of that would be 1. The m that's alone, the derivative of that would be 1. But we have to do implicit differentiation for related rates. So we're going to say the derivative of s is 1 times ds dt. And 1 times ds dt we could just write as ds dt. Okay. Then if we take the derivative of 50t squared, we get 100t. And this right here is the velocity equation times dt dt. This one we're not going to do dt dt because that's the rate of change of time as time changes, which is kind of weird.
Why would it be d theta dt?
Because there's no theta in this problem.
Oh,
Okay. So this gives us ds dt is the rate of change of the rocket. It's the velocity of the rocket, right? So this is the position equation right here. This is the velocity equation right here. We could also have called it S prime. Okay, so if I wanted to solve for ds dt when t equals 10 seconds, what do I do? Plug in 10. So ds dt evaluated for t equals 10 is 100 times 10, which is what? 1,000. And what are the units? Feet per second. Okay. And it would be just feet per second, not feet per second squared, and that's because feet per second squared is acceleration, not velocity. Okay, so feet per second would be our velocity. Okay. Okay, so we have a big long list of things that we know. Okay, so let's go ahead and think back to what the problem was actually asking. It says, what is the rate of change of the angle of elevation? So that means we are finding d theta dt, and that means that the formula that we're using has to have a theta in it. So what formula are we going to use? Tan theta equals s over 2,000. Okay? So the formula that I'm using is tan theta equals s over 2,000. All right, now if I don't want this to be a quotient formula when I take the derivative of it, how could I rewrite this? Tan theta. Now I'm not going to do it to the -1 because that's what we do with variables. I'm going to pull it out like a coefficient. So this is 1s over 2,000.
So it's s equals 2,000 times.
It is 1/2000th times s.
Okay.
1/2000th times s.
Why did you do it to the negative power again?
We only do that with variables. We don't do that with numbers. And that's because if I do 2,000 to the -1 power, that's just 1/2000th.
Okay.
So I just write it as 1/2000th because it's a number. Okay, we're going to go ahead and take the derivative of this because that's what we do with related rates. We figure out what our formula is or our equation is that we're working with, and then we differentiate it, and we just make sure that when we differentiate it, we add the d whatever dt to each variable. Okay, so the derivative of the left side says the derivative of tan. Anyone remember the derivative of tan? Secant squared. So we're going to say that the derivative of this is secant squared theta times, what's the derivative of theta? D theta dt equals the derivative of 1/2000th times s is 1/2000th times ds dt. Okay, so we're going to go ahead and plug in what we know. Okay, I know that this is 1/2000th, and you guys know how we were doing in the video. I made you guys plug in the notes or the units with the numbers.
Yeah.
We know that when we get done with this, our unit of measurement is going to have to do with radians, right? Because when we do calculus with the different trig shortcuts that we know, our trig shortcuts only work in radians. So our unit of measurement is going to be radians for sure. And it's radians per what unit of time? Second. We know our numbers are going to be an answer in radians per second. If the numbers we're plugging in are all in terms of feet and feet per second, and I don't know how to explain that unit of measurement change to you guys. But we can know just by looking at the problem and by what they're asking that our unit of measurement should be radians per second. I know that it's radians per second and not degrees per second because we use the calculus shortcuts for derivatives that have to do with radians. If we wanted to get degrees per second, we would have used different derivative shortcuts, okay? So as soon as I said the derivative of tan is secant squared, as soon as I said that, my problem was in radians. Does that make sense? So I'm not going to include my units this time only because I know the final answer has to be radians per second, okay? So ds dt is what? 1,000. I'm going to go ahead and leave off the feet per second. D theta dt is what we're solving for. And secant squared is actually kind of the weird part because we think that we don't know it, but we actually do because we have the triangle. So think back to SOHCAHTOA. Secant is the flipped version of what? Cosine. So yeah, so it's 1 over cos, or it's if you take cos and you flip it. So instead of being adjacent over hypotenuse, it's going to be hypotenuse over adjacent. So what's the hypotenuse of our triangle? The hypotenuse is square root of 29 million. I'm so glad we get to use that number. So there's hypotenuse over, what's our adjacent side? 2,000. Okay, so we have secant squared, which means we have hypotenuse over adjacent, and we are squaring it. It's going to get rid of the square root, but it's also going to square the 2,000. Okay, so don't just cross out your square root. Be careful. Okay, so I'm going to go ahead and I want the d theta dt to be by itself, right? What is 1,000 multiplied by 1 over 2,000?
1 over 2.
Yeah, it's 1/2, right? Okay, so I'm going to say d theta dt equals 1/2, just because that's a little bit easier to type in, divided by, and I'm literally going to put it like this because I just don't want to mess with this, to be honest. Is it a nice decimal to deal with? Yeah. Okay. All right, so when we type that into our calculator, and if you want, you can use the fraction function of your calculator. Do you guys know how to do that? So we hit alpha y equals. And on the top, I'm going to type 1/2. And on the bottom, I'm going to type square root of 29. 1, 2, 3, 4, 5, 6. There's 29 million divided by 2,000 to the second power. And this is my decimal answer. I'm going to just check and see if I can make it a fraction answer, because it could be. So this is 2/29. And what did we say our units would be? Radians per second, because it's a rate of change. Or I can go ahead and write the approximate answer, 0.069 radians per second. Both of those are equally accurate. On the AP exam, they would accept both of those answers as being correct. Yes?
So problems like this, where there's going to be like say decimals or like really big numbers like that, we will be able to use a calculator on this one?
Yeah, if I were to give you a no calculator problem for this, I would make sure that the numbers kind of work out nicely, which is almost, that's how you can kind of tell if you're doing it right or wrong, is if your numbers start to get real messy, like this was not right. Yeah. Because I'm not evil with the no calculator problems. And they are maybe a little bit evil sometimes, but they are mostly not evil. Okay. All right. I know that one was probably a little bit more uncomfortable because the formulas were less were less straightforward. But what I will say is what I've noticed, typically they don't do this where they give you a different formula up here. Typically when they do these angle of elevation problems, I'm noticing it's a mixture of the Pythagorean theorem and SOHCAHTOA. Does that make sense? So I would maybe write a note to yourself on here that anytime they talk about the angle of elevation, you need to use SOHCAHTOA because I think that's really easy for us to forget. That makes sense? Angle of elevation problems, SOHCAHTOA. And if you notice, we did use SOHCAHTOA twice. We used it once to know that we were doing tan theta equals S over 2000. We did it again when we figured out what to plug in for secant squared. Okay? Now, technically, you could have used sine theta or cos theta as well. Does that make sense?
Yeah.
Okay. All right. Actually, probably not cos theta because those were both constant numbers. But as long as you use the opposite side, as long as you use the S. Okay, we got one more problem. Say it again. Technically, yes. But I don't feel like writing a sentence there and I don't have a lot of room. Also, for the assignment we're doing in class today, you don't have to write sentences because there's definitely not room. So, maybe before you move on to the next problem, think the sentence in your head and then move on. So at least you know how to interpret it in a sentence. All right, number 6. Before I read this problem, yes, I understand how stupid it is. Okay, let's go. A man is sipping a soda through a straw from a conical cup. Conical? That means that he's drinking soda out of a cup that looks like this. Yes, I recognize how stupid it is. Okay? Because literally no one would ever do that. How would you put your cup down? Yeah, the leftovers of a snow cone. Okay, so here's the cone. It says that the cone is 15 centimeters deep total and 8 centimeters in diameter at the top. I'm going to put a radius of 4 right there. So it says when the soda is 10 centimeters deep. So we're picturing like, here's our soda. Look how good I'm at drawing, you guys. Also, the soda has waves. Because that's how soda works.
That's how waves works. I want to have waves.
Yeah. So when the soda is 10 centimeters deep, what variable does that go with when the soda is 10 centimeters deep? That goes with the height. Okay, so we're going to say the height is 10 centimeters. He is drinking at a rate of 20 centimeters cubed per second. When it tells you centimeters cubed, what is centimeters cubed? What unit of measurement is cubed? Volume. Okay? He is drinking at a rate of 20 centimeters cubed per second. So if it's a rate of volume, then what should we write?
Plus 20.
No. What variable? So we know it's a variable v, but it's not just plain old v, because that would be, it's dv dt. The reason that I knew it was dv dt and not just v is because it doesn't just say centimeters cubed, it says centimeters cubed per second. So that tells us it's a rate of change, it's not just a volume. Okay? So 20 centimeters cubed per second. Okay. How fast is the soda level decreasing at that time? So what variable does that have to do with? The soda level. dH/dt. dH/dt equals what? Okay. So this has to do with volume. The shape is a cone. So we need to know the formula for the volume of the shape of a cone. Okay, let's Google that. I'm not kidding. Get your phones out, Google it. Volume for a cone.
The formula
On the AP exam, are they going to give us the formulas?
Typically, they give you these formulas.
Okay.
It's not 4/3 pi r cubed. That's a sphere. Okay, so we're going to call it 1/3 pi r squared h. All right. Now, did they ever talk about the radius of the liquid?
No.
Did they talk about the radius of the liquid changing? So we don't want that r in there because we don't have information for that r. Does that make sense? We know that the height of the liquid is 10. We know that we're looking for the rate of change of the liquid, but we don't know what the radius is at that time or what the rate of change of the radius is. So this is a common cone problem where they tell you the radius of the original shape, but they don't tell you the radius of something later, and that means we need to eliminate the radius as a variable. So we're going to write a proportion. We're going to say the radius as related to the height, and we're going to relate that back to the original information they gave us. That was that the overall height of the cup is 15, and the radius of the cup is 4. So we're going to say r over h equals 4 over 15. Yes, ma'am?
On the test, will they be given the volume?
Yeah, so what I've mostly seen is they typically give you the formulas for these, or they do a situation where they give you a different formula to use, but they typically write it out. Because they're not testing whether or not you know these formulas, they're testing whether or not you can do the related rate process. If it's a formula they think you should know, they're not going to give you the Pythagorean theorem. They're not going to give you the area of a circle. They're not going to give you the circumference of a circle. There's things like that are pretty basic. But volume of a cone, I think they typically give you. Volume of a sphere, they're going to give you things like that. Yeah.
Can you please explain the R rate again?
Yeah. I'm writing a proportion relating the radius of the cup to the height of the cup. And I'm just showing the relationship between those two numbers, and you'll see why in a second. So in general, I'm saying radius to height. In this particular example, it's 4 to 15. Okay? Now to solve this equation, I'm going to cross multiply. So I have 15r equals 4h. And I'm going to solve for r so that I can take the r in the equation and replace it with something that's in terms of h. That way I'm completely eliminating that variable in the equation. Okay? So I'm going to divide by 15. So r equals 4h over 15. So this is a pretty common process in these problems to eliminate the radius in the equation. This is common. Okay? All right. So I'm going to take my volume equation and I'm going to write 1/3 pi, and instead of writing r squared, I'm going to replace that r with 4/15 h. And that's going to be squared, right, because it says r squared, multiplied by h. So I'm not taking the derivative. I'm simply rewriting the formula so it only has h's, it has no r's. Okay. Make sense? Okay. All right, now I need to simplify this a little bit. So I have v equals, let's go ahead and in our calculators we can do 1/3 times 4/15 squared. 1/3 times 4/15 squared. And I don't want that decimal, I want the fraction.
4 over. I got 4.
Did you type it in as 4/15 squared?
LOL.
I got 16 over 665. 675.
Yeah, 16 over 675. Okay, so the fraction is 16 over 675. We still have that pi that was sitting right there. We also have an h that's been squared, and we have an h to the first power. So overall, what do we have? H to the third. Okay, so that is the formula that we're working with. So to get this in my calculator, I typed 1/3 times 4/15 squared. 1/3 times 4/15 squared. So I was just simplifying, I was just cleaning it up so it looks a little bit nicer. Okay, now we are ready to take a derivative because we always do that in related rates. We have the formula that we're working with, and we take the derivative of it, and we make sure we do implicit differentiation for each of the variables. Okay, so the derivative of v, dv dt, and the derivative of 16 over 675 pi h to the third is, 3 times that fraction and the pi, h to the second, times dh dt. Okay. So I'm going to go ahead and take that fraction and just multiply it by 3 and see what I get. 16 over 225. Okay, so I'm going to plug all my numbers in with that new fraction that I have that I simplified. Okay, dv dt I know is 20 centimeters per second. So I'm going to write 20 centimeters cubed. 20 centimeters cubed per second equals 16 over 225 pi times, and what am I plugging in for h? 10 centimeters, right? I'm going to put my units in there. So basically the only time you would not put your units in the problem is if you're doing an angle of elevation change. Okay, the rest of the time you can put your units in. dh dt. And I'm going to go ahead and clean this up a little bit. So I have 16 over 225 multiplied by 10 squared is 64/9. So I have 20 centimeters cubed per second equals 64 pi ninths. And I had centimeters and I squared it. So that's centimeters squared. Times dh dt. I was like, well, this is getting awkward. I'm going to stop waiting. Okay. So the only reason each of the steps looks like a lot different is because I'm just cleaning up the numbers as I go. All right. So what do I do to solve for dh dt? Yeah, I divide by 64 pi ninths centimeters squared. Divide by 64 pi ninths centimeters squared. And the nice thing about these problems is you can literally write that your answer is 20 divided by 64 pi ninths and get full credit. So if you want to leave it as that, you can, but I'm like, ooh, what does that actually mean? So let's go ahead and plug that in and just see what the approximate answer is. So we've got 20 on the top. On the bottom, we have 64 pi ninths. Ooh, there we go. So 0.895 centimeters per second. So if we look at our units, we have a centimeter squared on the bottom, and we have a centimeters cubed on the top.
So would it be centimeters per second?
Yep. I don't understand why kids do that. It's like they're thinking, I'm going to get out of class and act like a herd down Harrison Hall.
It's fun.
Why is it fun?
Because I run out their halls.
Just very strange. All right. So that's your unit of measurement is your centimeters per second. So that means that at the moment in time, when the height of the soda in your cup is 10 centimeters deep, at that moment in time, the soda is decreasing in height by 0.895 centimeters per second. All right, now I need you to go back real quick. This volume was decreasing, which means what sign should it have had in front of it? A negative. Okay, so we're going to go through, we're going to fix that because I was not thinking and I missed that. So there's our 20 right there. Go down here, here's where we plugged it in. The volume of the soda was decreasing decreasing because we were drinking it.
So wouldn't a number have came out negative?
It's going to have come out negative, so we're going to fix all of them. So there's a negative 20 right there. Here's the negative 20 right here. Here's the negative 20 right here. And so that means that the height is decreasing.
Okay.
Because we're drinking it. Our volume is decreasing, our height is decreasing.
Can we write this in now?
Yeah. All right, let's write out the sentence.
Yeah, I wasn't gonna wear it.
Okay, so at the moment, when the soda has a height of 10 centimeters exactly, at that moment in time, the height of the soda is decreasing at a rate of 0.895 centimeters per second. Notice I did not say it was decreasing at a negative rate, because that's a double negative, that means it's increasing. I said the word decreasing and did not put a minus. Did you guys notice that?
Yeah.
Okay. The other way you could phrase it is you could say it is changing at a rate of negative 0.895 if you wanted to put the negative in there. Okay. So it's decreasing at a rate of 0.895 centimeters per second, or it's changing by a negative rate.
But you wouldn't say increasing at a rate
Of negative. That would be so weird. They'd be like, where's your brain? Come on. Think about what you're typing, or what you're writing. Okay. Yes.